Again, thank you for this introduction, and I'll get right into how I think compressed air energy storage should be considered and taken seriously to be investigated for our energy supply future, our energy supply mix. So a couple of just simple observations. Solar and wind are the cheapest form of new electricity generation available and have zero emissions, zero direct emissions. And of course, both solar and wind generation are intermittent and require energy storage in order to smooth that electricity over fluctuating demand periods. And to facilitate large-scale development of renewables, long-duration energy storage systems are required. So why do we need energy storage? In this chart here, I'm trying to show just a model 24-hour period along the bottom axis and energy requirements throughout that day on the left-hand side. And you can see the double solid line. The base load represents that power generation that must be generated continuously all the time to satisfy our basic load. And then the grid demand line is the dashed brown line that actually represents what the load looks like throughout the day. Again, this is a simple model. And that grid demand varies on time scales from literally minutes to minute, and then seconds, and then to days. So this is the load that SAS Power Generation has to follow in order to meet all the requirements. So I'm going to lay over an example of, in this case, a solar generation profile. And you can see like from 8 in the morning till 4 in the afternoon when that energy is available. And there's 2 points here to make. On either side of that green section, the area is blank underneath the demand curve. And so this is electricity that's not being provided by the renewable. And at the same time, above the grid demand curve, there is an abundance, an excess of renewable generation. And although we don't have this issue too much in Saskatchewan, in jurisdictions where there's significant renewable development, particularly wind, there are periods when there's actually too much generation. And in Alberta, this is common in Alberta and Ontario, California, these kinds of jurisdictions. So the idea of energy storage is to take that renewable energy above that grid demand curve, which would otherwise be curtailed, and move that into storage that's available in the next portion of the generation cycle. That way we can actually fill in and help support grid demand by storing that renewable energy for a period of time. Along the bottom, you'll see some yellow bars start to come up. That represents, in my idea, is that if we roll out significant portions of renewable energy with compressed air storage, then in fact, we're actually starting to build out baseload capacity with CAES. This next chart has power on the left-hand side and energy on the right, which refers to the duration. And of course, the area we're mostly familiar with storage is batteries. And batteries occupy kind of the left lower quarter of this chart, and compressed air the upper right quarter. Lithium-ion batteries are useful for high power, but low duration, usually measured in hours, provide excellent peaking operations and ancillary services. But the cost increases linearly with duration. To double the capacity essentially doubles the cost. You just have to proportionally add more batteries. CAES occupies a different space. There's some overlap, of course, but CAES is referred to, is available for high power, hundreds of megawatts potentially, and long duration for many, many hours, many days even. And as we'll see in a few moments, we can essentially double or increase that duration capacity with modest additional capital cost. So how does CAES work? This is an example of where we have direct generation from sun and wind power being fed directly into the grid as that's available and as the demand requires it. In situations where there is excessive wind and solar generation, and it exceeds the requirements of the grid and could otherwise be curtailed, we take that energy and use it to compress atmospheric air into rock salt caverns that have been purposely built in the subsurface. So we're just taking atmospheric air and pressurizing it in these giant subsurface containers. And then later in the generation cycle, we're releasing that air in a controlled fashion through an energy generating turbine, which sends that electricity to the grid. CAES is not a new technology. The image on the left is a 290 megawatt CAES plant at Huntorp, Germany, developed in 1978. And on the right side, a 110 megawatt CAES plant at McIntosh, Alabama, developed in 1991. So caverns have been used, salt caverns have been used since 1978, providing industry over 70 years of operational experience. The two plants that I've talked about at Huntorp and McIntosh use what's called a diabatic CAES system. Diabatic means during the generation phase, a small portion of natural gas is required to prevent freezing and to add some boost to that energy. And if we were to develop that technology now based on modeling, a new diabatic system would be cost competitive with new combined cycle gas turbine generation, while providing an 80% reduction in CO2 emissions. But of course, we're looking for 100% reduction. So an adiabatic CAES system is more expensive. It includes additional technology, but produces zero greenhouse gas emissions. And this would represent a second generation. And the difference between the two is that during the compression stage, there's significant heat created by the compressors. And that in the adiabatic system, that heat is captured and is made available during the generation stage later in the cycle, therefore avoiding the use of natural gas altogether. So a little bit of geology now. If we were my background is drilling wells. So as we drilled into the subsurface, we penetrate various layers of rocks. They just kind of envision them like pancakes, and each layer has its own geological character. And some of these are oil bearing, gas bearing, potash bearing. These are just some of the common names: Manville, Dawson Bay, Deadwood at the bottom. And the pink section in the middle refers to the prairie salt section. And that's a very thick section of salt in areas that is marked by, it's useful particularly because at the top in certain areas, those three green bands represent potash layers. And this is where we're mining potash in Saskatchewan. Otherwise, the prairie salt is predominantly just that. It's predominantly sodium chloride. It varies in conditions, of course, from area to area. And where the area is suitable, after a thorough assessment of what the conditions are with that salt, we can develop salt caverns. And what's involved in developing a cavern is simply drilling into the salt and circulating warm, fresh water to create a cavern, a void within that salt. And that's done in a very carefully mined way to control the shape and size of that cavern. Now, not only do we create a lot of what's called brine, which is very salty water in that process, and we have to get rid of that. So again, in the appropriate location, that deadwood, and there are other zones, but predominantly the deadwood, can be used for that brine disposal. So we are really blessed with two geological features here: the salt to create caverns and mine potash, and a place actually at the same place, same surface location, we can create a well for brine disposal. Our potash industry in Saskatchewan would look very different if we did not have the ability to dispose of this brine. So again, I'm just pointing a plug for geology here. So once surface infrastructure is in place, we could add capacity by developing additional caverns. This image is it's actually a sonar image of the Transgas Asquith salt cavern. This cavern is used for storage of natural gas. And in this case, it's about 70 meters tall, 64 meters wide, at an average depth of about 1,100 meters. And this cavern can contain about 5 million cubic feet, or 139,000 cubic meters of natural gas in this case. This is a map of the southern portion of Saskatchewan, and the colored areas represents where that salt is. And again, we know this from the drilling of thousands of oil and gas and potash wells in the province to delineate where this is. The warmer colors just represent greater depth. So at Saskatoon, kind of in the middle of all that color, this top of the salt is at about 1,050 meters. And at Regina, it's a bit deeper at about 1,650 meters. The stars represent locations where we have developed caverns. Since 1958, there's been 58 caverns developed right across this band of salt, right from Lloydminster on the west side to Mooseman on the east. There's several caverns at Regina, not far from Saskatoon. So we have this operational experience at developing caverns. This is the same map generally, but what I've done is overlaid the major transmission lines that SaskPower has throughout the province. And I'm really just trying to illustrate how these resources kind of stack up, where we have the salt, we have the capacity to build caverns, and we have transmission lines and generating locations where all these pieces can fit together to try and narrow in where this technology might be most useful. So compressed air storage is an excellent, in my opinion, it's an excellent storage option for Saskatchewan. It has a very small surface area. All the storage is underground. These salt tanks are very, very large, and you can't see them because they're underground. The geology is well understood. We have drilled over 170,000 wells in Saskatchewan historically, and have been operating these caverns since 1958. We have highly skilled oil field industry trades, and the regulatory infrastructure is generally in place. These caverns are operating using combustible natural gas, of course, but in the case of a compressed air storage, we're looking at atmospheric air, which is non-combustible. So, in my opinion, wind plus CAES can provide firm capacity power if it's managed as this appears to be. I use wind and CAES because wind is it's not so seasonal as solar, that it operates at night, that kind of thing. But of course, solar can play a significant role in this as well. And very importantly, there are no toxic waste or legacy disposal reclamation issues with compressed air storage. At end of life of a facility, there would be the usual reclamation issues with a large plant of some kind. And we have high quality geological sites. We have the resources to do this in Saskatchewan. So if we consider wind and solar and CAES as a storage facility in Saskatchewan, we have excellent feedstocks. We have cheap, unlimited wind and solar resources. With storage, we can facilitate large-scale renewable generation development now as well. Of course, one of the reasons we haven't developed our renewable resources to the extent that we could is in the absence of storage. But for example, a 300 megawatt CAES facility would require the co-development of about 1,100 megawatts of wind capacity. So if there were several of these plants to be developed in Saskatchewan, that opens the door for the construction and operation of thousands of megawatts of wind and solar capacity. A few summary points. Wind and CAES technology is simple, well understood, cost effective, and can provide long duration, firm capacity power. And this technology is available now. It can be scaled from 160 to 320 megawatt capacity, providing 60 plus hours of duration, depending on all the pieces are fit together. This is a big capital project. Each 300 megawatt facility would inject over $1 billion into Saskatchewan's economy, providing 950 construction jobs for several years, plus full-time operational jobs. This is typical of a large project like this. And each facility would require the construction of, again, 1,100 megawatts capacity of wind generation, and this could be done by third-party investors and developers, injecting up to $1.7 billion into the economy of several rural municipalities where these solar and wind generating operations would be developed. So if our objective is to deploy technologies to significantly reduce greenhouse gas emissions with the lowest cost to consumers, I think there's generally three on the table right now that can contribute to this objective. We have carbon capture, utilization, and storage. Based on the work of others, of course. This would have a levelized cost of about $82 to $140 per megawatt. This excludes storage. Carbon capture, CCUS in Saskatchewan would rely on imported gas. Saskatchewan currently produces less than 50% of the gas we consume. So as we develop additional generating capacity from gas, we are actually will be importing much of that gas from Alberta and probably BC. Small modular reactors are also being considered. It's currently an unproven technology with a high capital costs, and there's some uncertainty what the estimated levelized costs will be. And we have compressed air energy storage with renewables, which is a mature technology. A levelized cost between $91 and $114 per megawatt hour, and it uses unlimited cheap Saskatchewan renewable fuel. And local renewable generation development supports economic activity in rural Saskatchewan. This refers to the wind generation development that would be required. I've tried to summarize capital and levelized cost of electricity for a sample 300 megawatt facility. Based on research from the SMR Roadmap, Economic and Finance Working Group of 2018. SMRs, first of a kind, average capital cost from that document would indicate about $3 billion, with a levelized cost of generation at $52 to $110 per megawatt hour. In March of last year, Minister Morgan announced that capital cost would likely be closer to $5 billion. We are yet to, I don't believe we have it's been provided what that levelized cost estimate would be. I may be wrong on that. We have combined cycle gas turbine generation with carbon capture. Excluding storage, that's a little under $1 billion for the capital cost, with an estimated levelized cost of electricity of $82 to $140 per megawatt hour. This is from the US EIA document of 2020. And we have adiabatic CAES, which is a little over $1 billion for a 300 megawatt facility, with an estimated levelized cost of electricity from $91 to $114 per megawatt hour. This is particularly important to us as citizens because that generation cost directly reflect what we pay as individuals, businesses, and industry for the electricity that's being generated. By the way, that CAES adiabatic system has been modeled by a company called RMP Energy Storage from Calgary. They are a storage developer. All three technologies are potentially available to us, and I would also like to suggest that it's all three will have their place. I think the capacity, depending on the actual location and load requirements, all three generation technologies have potential. With the addition with CAES technology being able to ultimately provide storage services to the other two through SMRs and combined cycle, as they would like to be operating at a base load rate and may require storage services as well. So I'm hoping that I provided enough information to have us seriously consider how compressed air storage could potentially fit within this energy supply mix in Saskatchewan. I believe it does. I think there's lots of information. All these sources are different sources, so this is a very high level idea of what these costs might look like. So I think some real effort into doing a really good comparison, an objective third party, an objective comparison of these costs would be valuable to us. So with that, I am happy to take any questions.
Awesome. Thanks, Brine. I think there's a couple questions here in the queue, and I'll open it up to questions at this time. So a couple of the ones that have come through. Is there a specific reason the CAES is being looked at here as opposed to other long duration energy storage technologies such as pumped hydro and flow batteries?
I can't speak to the flow batteries particularly. I don't know enough about that technology. Pumped hydro is, you need some relief for pumped hydro to operate. And in southern Saskatchewan, where most of the load is, of course, we we don't really have the relief, the topographic relief, probably to make pumped hydro very attractive. So it's kind of the topography of southern Saskatchewan is probably not suitable.
Okay, we touched on it. You touched a little bit on your presentation on the price. So, is there any opportunity for CAES to provide ancillary services in Saskatchewan, such as frequency support, transmission support, decongestion as a non-wired alternative?
I'm not sure what a non-wired alternative is.
Non-wires alternative. I don't know if there was a.
Anyway, the ramping capacity of CAES is very flexible. These systems can ramp up and ramp down quite quickly, and so their capacity for load following would be, I think, very favorable. If that perhaps answers what they're getting at.
Okay. And do we need to create new caverns, or can we use the gas storage caverns or retired sections of potash mines here?
The shape of the cavern matters. They tend to be vertical in order to be structurally competent. Potash operations, those solution mining situations are more like horizontal. So the geometry of the cavern would be important. I think it could be explored in the future, but we have good experience with vertically shaped caverns that we should probably stick with to begin with. But there's research going into developing horizontally shaped caverns as well. So that's a possibility. Existing caverns, in the most case, if they're sometimes caverns start to leak, and that usually represent end of life for a cavern, and they can be used for other things after that. Most often, it's used for waste disposal. But if a cavern is airtight and operational, it's a very high value. So it would be, unless there was a reason, a non-economic reason, it would likely would not be available.
Okay, and touching on that point too, in terms of shape, but are there any other particulars that make a salt cavern a good fit for this?
Well, it's determined by the type of the geology. Many salt caverns are common around the world. They're used in many places, and their shapes vary depending on the body of salt they're dealing with. In Saskatchewan, we have what's called bedded salt, which tends to be widespread, but not that thick, relatively speaking. So we're limited in the size of the caverns, the size and shape of the caverns, based on what the geological conditions are. But again, we have abundant experience in Saskatchewan with what we have. You kind of have to use what you have, but we have that experience in Saskatchewan.
Awesome. And here's a question: when you take 1 megawatt of power from wind or solar, then compress it and run it through a turbine, how many megawatts do you get out of it?
That's more on the power side, and I'm less functional in that area myself, but I believe there's about a 65% round trip efficiency. Again, this is based on information that I've read about this with RMP Energy Storage.
Thanks, Brine. And then in terms of talking about the price per megawatt, so does the 91 to 114 megawatt price for clean, firm generation from CAES include both the renewable generation and CAES, or just CAES?
That is based on a contracted purchase price, I think between $35 and $40. No, I'm sorry, I shouldn't quote that because I don't know exactly, but it's based on a contracted commercial purchase price of renewable generation. So the fuel is included in that cost, yes.
Thanks. New question just popped up. I think we ran through most of them, but are there incentives or policies available that could be implemented that would help increase the development of CAES here in Saskatchewan?
There might be. There are several federal programs that are trying to encourage the development of new energy. And although I don't know the details of it, there's been a recent tax-based incentive to develop new energy profiles. So there could be. I don't know exactly though.
Okay. Just trying to think, see if there's anything else that we could answer, but think we're right about on time now. So, Brine, we appreciate your time here today and your presentation. And everybody, thank you for your questions. If you do think of something after the fact, after we get offline today, you can always go to saskpower.com/engage and use the Ask a Question feature. People like Brian are on the back end and happy to answer any questions or comments that do come through in the future. So with that, we'll allow everybody a little bit of time to get to their next session. But again, Brian, thank you so much for your time, which we very much appreciate it.
My pleasure. Thanks, everyone, for your attention.